we are picking up on Newton's laws. So they are discussing the causes of motion, or really what causes motion to change. The first law says that stuff doesn't really like to change its motion unless you apply an outside net force. If you don't, then stuff will keep doing whatever it was doing, whether that was remaining at rest or moving at a particular speed in a particular direction. We call that property of stuff inertia, that it is generally inert to these changes in motion, doesn't like to do it. There's not really a deeper explanation than that. If you go deeper in physics, no one ever says, and that's why stuff has inertia. It really just is this general property, and we just know it to be the case for everything we've looked at that has mass. The second law says what happens when you do have a net force acting, and that is an acceleration, a change in the velocity of the object. That could mean changing in speed, direction, or both. The size of that acceleration is directly proportional to the net force that acts, meaning you double one, you double the other. And it is inversely proportional to the mass, so the larger the mass, the smaller the acceleration. We're generally going to look at that as two separate components, though, one happening in the x, one in the y. And we're going to apply that with free body diagrams, which is what we started drawing here. So free body diagrams are just listing all the forces acting on an object in a sort of organized way, and then using it to find the components of these forces, add them up to get the net force, and then apply the second law, or first law, depending on the situation. So that's where we were here. We need to find components for each of these forces. So this is just like for displacements. You find components in the exact same way. So someone tell me for the components of that weight vector W, tell me, are they positive, negative, or zero for both the x and y? And by the way, I didn't.
Zero
0
Oh yeah, go ahead.
for
So
the X,
zero for the
0
x.
for the X, and negative for the Y.
Yep, perfect. All right, so um, it is downward. In the y direction, it doesn't point in the x direction, so yes, those are our components. What I was going to say is every time there is a long pause, I got to edit it out in post, and that takes time each time, so um, don't make me do that a lot. Help me out with these, because I know you're fine on these. So, next one is drag. Someone tell me about the components of that drag force.
Is the drag negative and the y component 0?
Yep, perfect. So it points to the left, and then that's 0. So I'm leaving it general. FD is the magnitude, the size of that drag force. It's just the number associated with it. And then the hardest one is the ground reaction force, F ground. Someone tell me about the signs of those components.
Wouldn't they both be positive?
Yep. So it points to the right and it points upward. And then it's just a question of whether after the magnitude we have a sine or a cosine. So we know it's magnitude times something. So for this x component, someone tell me about whether I should use sine or cosine.
Cosine, since it's adjacent to that angle.
Yep, perfect. And then that leaves sine for the other one because it is opposite the angle. And now we've got everything we need to find the net force. It is F ground cosine 80 minus FD in the x direction. And then in the y direction, F ground sine 80 minus W. All right, what do we do with that? Well, we know this whole thing is our net force in the x direction. This whole thing is our net force in the y direction. The question is, what is their horizontal acceleration, ax? So, we just say, well, the net force in the x direction is F ground cosine 80 minus FD, and that is equal to the mass of the object times its x acceleration by Newton's second law. Net force is always equal to mass times x acceleration, and then same for y. And so, we're just concerned with the x piece in this question. So we solve for x acceleration. F ground cosine 80 minus FD over the mass. And we come back up here, we see that F ground is 2,500 newtons and FD is 6 newtons. So we'd put that in here, 2,500 newtons, 6 newtons, and their mass was 95 kilograms. So we get an x acceleration of about 4.5 meters per second per second. And we can kind of read off directly what's physically happening there. This says the x component of that ground reaction force is what's moving them forward, accelerating them forward. The drag force is limiting that, subtracting off from it. The mass is also limiting that acceleration by dividing through by it. All right, so that is a forces problem. They all go like this. There could be more intricate sort of variations, but it's all this sort of process. So hopefully by the end of the chapter, you'll see we're just kind of doing the same thing over and over. All right, the third law is the hardest one, to be honest. Mainly conceptually, because it's the easiest one to kind of miss something or mess something up. So the first two are about the forces on one object, a single thing. The third law is different because it's about the forces between different objects. It's sort of what connects your object you're looking at to the outside world. So this is about interactions between different things. And you've definitely heard this stated in a way that I don't actually like. It is the action, for every action there is an equal and opposite reaction. So when one object exerts a force on another, you call it the action. The other object exerts an equal and opposite force on the other, which we call the reaction. Or as an equation, if A exerts a force on B, B exerts a force on A of equal size, but in the opposite direction. Same vector, but flipped over. The reason I don't like the action and reaction phrasing is because it makes it sound like the reaction comes later. That's what reaction usually means to us. But action and reaction happen at the exact same time. There is no cause and effect for this. It is just when one happens, the other always happens at the exact same time. So I kind of say just force A exerts on B is negative to force B exerts on A. There is no cause and effect. All right, so we're going to look at some cases of that get sort of increasingly upsetting. The last one, you're not going to want to say it, but it is the same rule as the first two. So let's say we've got a car driving along a road. The action is, as the tires of the car rotate, they push backward on the road. So this will be the force the car exerts on the road. What is the reaction to that?
The car moves forward.
Yeah, let's phrase it a little more in the same way that the action is phrased.
The road pushes forward against the tires.
Yeah. Say the road pushes the car forward. That is the force the road exerts on the car. And this is where, I mean, it's kind of tempting to say one came after the other. It kind of makes sense. Car pushes the road, and then the road pushes the car. But it is simultaneous. They are happening at the exact same time. So these are vectors of equal size, but in opposite directions. The only one that influences the car is the red one, the one pushing on it. And so it's what would show up in a free body diagram of the car. If we were drawing a free body diagram of the road, we'd use the blue vector, because that's what's acting on it. That's the confusion that can happen a lot with the third law, is which vector goes in your free body diagram depending on what you're looking at. Alright, next one. A plane's wing moves through the air. As that wing moves through the air has to pass by it, and that's going to deflect some of the air downward, especially if you have this, what we call angle of attack to the wing. So our action is the wing is going to apply a force deflecting air downward. What is the reaction?
Does the air push the wing upward?
Yeah. So air pushes the wing upward, and we give that force a specific name. We call it lift. And that is, in a very summarized and sort of hand-wavy way, how planes fly, is Newton's third law. If you look into the full description, there's really a lot of moving parts going on and a lot of physical principles at play that are sort of happening simultaneously, but Newton's third law is the short and dirty answer to it. So this is the force the air exerts on the wing, and that's what we call lift. All right, this last one is the one I'm saying you're not going to want to give this answer, but here it is. When, say, you jump over something, or even if you're standing still, Earth is going to pull on you. It exerts a gravitational force on you. So this is the force Earth exerts on you. What is the reaction to that?
Is it that the Earth is somehow pulling you away or pushing you away?
Almost. So let's kind of read it the same way we have the others. It's the force A exerts on B is equal to the force B exerts on A. A exerts on B is Earth on you. What's B on A?
You on Earth?
Yeah. You pull the Earth upward. And with a force that is exactly the same size as the force Earth exerts on you. That one's kind of troubling, but it's the same statement as the other two. So, in all cases, the action and reaction forces are equal in magnitude. This is a line of text I've been meaning to write in for several semesters, and I forget every time. So anyway, let's look at that last case, because I know it's sort of like, that one doesn't sound right. What we have to do to sort of make it make sense is look back at the second law. So if we can agree that these forces are the same size, what is it that makes such a difference between me and the Earth? Because me, I definitely would move a lot in this scenario, but the Earth is, we don't notice it move, at least, hardly any. So why is that? What does the second law have to say about that? Well, let's compare accelerations. So for you, and I'm going to save writing acceleration because we want to sort of scale it based on how large it is for each of us. We're going to say for both me and the Earth, we just calculate the acceleration based on the force acting on it and the mass. So between me and the Earth, which one has a bigger mass?
The Earth.
The Earth.
Yeah, unbelievably bigger. So huge mass versus tiny mass. Okay? So who ends up with the larger acceleration? Me or the Earth?
You.
Yeah. I'm dividing by a small number. I'm not subdividing that force very much. I have a relatively large acceleration. The Earth has an enormous mass. It is taking that force that it's feeling and dividing by a huge number that's going to spit out a very tiny number. That's the explanation. Although me and the Earth feel the same force in this situation, it has a much smaller acceleration as a result, meaning it barely moves at all. If you did the math on this to compare the accelerations, ours is 9.8 meters per second per second. The Earth's is 0.00 followed by, I don't know, 10, 15 zeros. 1 meters per second per second. So it moves, but in such a way that we can't even notice it because it's like on the scale of atoms. All right, and last application of this is rocket propulsion, because in that case, there is nothing else present to push you. If you're in empty space, where is an outside force coming from? The only place it could be coming from is this action-reaction interaction. In this case, it's that as the engine expels exhaust, the combusted fuel, whatever sort of liquid propellant it's got, the reaction is that the fuel propels the engine and whatever's attached to it, so the rest of the rocket, forward. So in this picture down here, we've sort of got several vectors representing that expulsion of fuel. This is the force the engine exerts on the fuel. The reaction is the force the fuel exerts on the engine. And so that's kind of the interesting thing about rockets is they work best in empty space. I mean, it makes sense that they should, but it kind of seems like it'd work better in air where you've got a lot of air to push on the rocket. In this case, though, really what you're trying to achieve is just expelling more fuel, and so it can push harder on the rocket. The air is just getting in the way of that. So that's why rockets work best in empty space. The last thing I want to show you about the third law is I really want to emphasize this line of action and reaction forces are equal in magnitude. That is always true. It's not like if you're very careful about how you jump, those forces will be equal. Or if the wing is at just such an angle, these forces will be equal. They are always equal. And so normally I would do this in person. We don't really need the sound because you'll be able to see what's going on. But what he's got here is two force sensors on carts, and they're each just measuring how hard each cart is being pushed. If the third law is true, we should see equal readings from each no matter what. They'll just be in opposite directions. And that's what the red curve here is and the blue curve. The green curve is the difference between the two. So it should be near zero. And that's what we'll see here in a minute. Back it up. So he's just pressing on them. And you'll see as time goes on, he just starts pressing any which way. In class, I just sort of hold them in my hands and press them into each other, however. Because it really doesn't make a difference what you're doing. The forces will always be equal in size and opposite in direction, so that that green residual curve is zero. Any difference is just sort of a calibration, like a reading issue, not a physics issue. All right, so questions on any of that so far?
You said forces will be equal in size and opposite in direction.
Yep, always. As long as it's an action-reaction pair, meaning it's always of the form FA on B and FB on A. Another example I could give is how we walk. When we walk, I push backwards on the floor pushes forwards on me. Those forces are always equal in size. And so, if you want to run, you want to get a larger force on you, you got to apply a larger force back on the ground. I could also come back to this wing example. So, planes can fly this way. Why can't we fly this way? By flapping our arms really hard.
Gravity.
Say again?
There's no gravity.
Well, gravity still acts on a plane, and they're much heavier than us.
Are we not exerting as much force as the plane?
Yes, that's kind of getting at the idea a little bit more. And the reason is the huge size of the wings means that they can hit a lot of air, a large mass of air. The more mass you're able to hit, the more force it's able to exert back on you. If you've got a tiny mass, it can't exert much force. It's like punching a tissue versus hitting a punching bag. Okay, the punching bag can exert more force on you, so you can hit it harder. There is a case where we can, quote unquote, fly. We just need something with a lot more mass to it, a denser fluid than air. That's what swimming is. Okay? You're flying through the water. You're generating lift from the water instead of the air.
I have a question.
Yeah.
So how would you explain like how birds fly then?
Great question. So for them, they have a smaller weight relative to that sort of surface area of their wings. So they can generate enough lift to overcome their own weight. And it's partly because birds usually have hollow bones or something else that just reduces their overall weight. And so in that case, flapping their arms is enough. For us, it's just the size of our arms, and then compared to our weight, we can't generate more lift than gravity pulls us down with. Does that make sense?
Yeah, that makes sense.
Okay. It is something that we had to look at and try and understand for a good long time to come up with the idea of flight. It was basically saying, well, we know we can't do it. We can't generate enough lift to overcome our own weight. How would we design a machine that can? And that's where planes come from, or helicopters, or any other sort of flying machine. All right, so if we look back at this example up here, this sort of tells us all the steps to applying Newton's laws. The third law just helps us in making sure we've got all of our forces listed down. So what I mean by that is, let's look at this guy that's running and see if we could figure out that all those three forces are acting on him without being told that they are. To do that, I just think about what it is he's interacting with in this picture. He's interacting with the ground, so he's applying a force to the ground, which means there should be one acting on him. He's interacting with the air, and so the air should be exerting a force back on him by the third law. He's also interacting with the Earth's mass as a whole through the gravitational force, and so he should be feeling a force from it as well. So the third law just helps you make sure your list is complete. All right. We're going to look at this sort of simplified picture because it lists several of the forces we'll see over and over. Let's say we got a block being dragged along by a rope. In that case, we'd have one force. Specifically in this picture, it would be tension, but we'll keep it kind of general, call it F1. We've got the earth pulling down on the block. That's the weight. And then the block's also interacting with the surface that it's sliding on in two different ways. One is what's keeping it from falling through the surface. If the surface weren't solid, it would just fall right down through. We called that part the normal force because it is normal to the surface, perpendicular to that surface. And then we've got this one to the left, that's the other interaction between the block and the surface that makes it hard for it to slide. So that's friction. Those are the main forces we're going to see over and over and over throughout the semester. So, how we analyze a scenario like this is we start by drawing a free body diagram after we've already drawn some sort of normal picture, but it was given here. And on that free body diagram, I'm going to transfer all my forces. So with this free body diagram, the next step is I need my axes. I sort of already chose them. It's just so I can put as many forces along an axis as possible. And then for any forces that aren't along an axis, like F1, it's at some angle to the axis theta, we need to split it into components that are along the axes. So F1x and F1y to form a right triangle. Again, the third law helps make sure we got all our forces listed. I look at everything the block's interacting with, which is a rope and the ground, and then the earth itself. Air, if we wanted to include drag in this, a lot of times we sort of forget about it, but it is there in the most technical sense. And then I just say, okay, that's everything it's interacting with. I think I'm done listing all my forces. Next thing is we need to find components of all of those forces. And that's where, at least up above, we used a table. You don't have to use a table, but it may help. So we got F1, F2, F3, F4, and the net force. Alright, so tell me about the components of F1 in this picture.
Would it be F1 x cosine theta?
So I think it's just because I wrote it that way. Technically, F1x is it's just F1 cosine theta.
Oh, okay.
Yeah, it represents that whole side length. But yeah, you got it. So it is cosine and it is positive. And then what about the y component?
Positive F1. F1 sine theta.
Yep. All right, and so how we're doing that is just remember how we find components. For the x, it's positive if it's to the right and negative if it's to the left. You use cosine if that component is adjacent to theta, sine if it's opposite. And then for y, positive means up, negative means down. And then use sine if it's opposite that component, cosine if it's adjacent, and the order of those is just flip-flopped because the top one is usually what you use, but it's not always. You got to be careful about how the angle's given. It's just, it tends to be given relative to a horizontal axis. Okay, what about F2?
0 for x and positive F2.
Yep. And here, I do get the question sometimes of why don't we use sine or cosine? You could if you wanted to. So in this case, we've got F2 is at 90 degrees to the x-axis. What is cosine of 90?
0.
0. And sine of 90 is 1. So we could have written it as, maybe don't write this because it'll look confusing later, but I could have written this as F2 cosine 90 and F2 sine 90. But cosine 90 is 0, so this whole thing is just 0. Sine 90 is 1, so it's just F2. So under the hood, we sort of are using cosine and sine still. It's just, to me, it's easier to just recognize none of it points along this axis, all of it points along this axis. All right, what about F3?
Negative F3 and 0 for y.
Yep. Alright, and finally F4.
0 for x and negative f4 for y.
Yep, perfect. And now we just need to use all that to find the net force in the x direction and in the y direction. And to do that, we just add. So we did the hard part, and that makes finding net force easy. I'm just squeezing it in there. Alright, then this is the new step. Everything prior is pretty much just vector addition as usual. The new step is if you want to find, say, some force you don't know out of that list, like you don't know the value of F1, for instance, you now have two equations that will let you find it. And that is what you get from either Newton's second law, which is to say the force is proportional to the acceleration if there is a non-zero net force, or the first law if you see that the thing is in equilibrium. It is either at rest or moving at a constant speed in a straight line. In that case, you can set the forces equal to 0. If you're not sure, that's why I say, or you don't know, just go with second law, and eventually you'll hopefully realize ax and ay are 0, because the thing's not accelerating. Then you're back to the first law anyway. So you can just always say equals ma, and then just decide that acceleration is 0 later down the road. We'll see that here in this problem here in a bit. So, our net force in the x direction is F1 cosine theta minus F3. That's equal to mass times x acceleration. Net force in the y is F1 sine theta plus F2 minus F4. That's mass times y acceleration. And then depending on what you're given in the problem, some of that you would know, and there would be something you don't, and you put all that together to find that unknown. Sometimes, since you've got two separate equations, you're dealing with solving a system of equations, which is unfortunate but necessary, and we'll see how that goes in a bit as well. You don't need to remember this necessarily, but I think it's interesting, and so of course I'll go on a tangent about it. Newton's laws don't actually always work. They are just an approximation to quote-unquote the truth, but they work very well for any everyday thing you're ever going to run into, unless you happen to be working on a quantum computer or something like that. It's just when you try and look at the extremes of scale that Newton's laws start to break down and not give you the right answer. Extremes like small masses, so electrons. In that case, we have a different theory of motion, quantum mechanics. If things are very large, like galaxies, the masses get astronomical in size. In that case, Newton's laws stop working, but we have a different theory for that, general relativity. And then for things that are going very fast and are massless, that's why they're able to go so fast, like light, we have special relativity. And one of the goals of physics nowadays is to pare that down even more, to have a general theory of everything. You hear it called that, the theory of everything. So far what we've done is quantum mechanics and special relativity you can put together to study very small things moving very fast. That's called quantum field theory. General relativity, they're trying to sort of put in with it, and then you would call that quantum field theory in curved space-time. There's also that strong nuclear force we talked about, and that's trying to get paired in, and that's when you get into something called the grand unified theory. And then the last bit is there is a problem of making very small stuff vibe well with this general relativity description of gravity, because that's really the issue, is when things get really large, the gravitational force is significant, and you start to see features you don't at the small scale. So, people are still trying to figure out what they call theories of quantum gravity. Very small stuff, but with this modern view of gravity. They don't vibe well still, and that's one of the big barriers in theoretical physics nowadays. Okay, tangent over. Let's look at the gravitational force in a little bit more detail. We're going to take each of those forces I listed above, gravitational, normal force, friction, and tension, and sort of look at each of them in more detail. So this law, the law of universal gravitation, could be considered Newton's fourth law, because he discovered it as well, but it applies specifically to gravity. So if we've got two point masses, two little concentrations of mass, M1 and M2, a distance r apart, the law of universal gravitation says that the size of the force between them, we know it's an attractive force. Gravity is an attractive force. It is proportional to the masses of the two objects, meaning the larger the mass, the larger the force. But the larger the distance, the smaller the force, so distance goes in the denominator. And it actually dies off faster than you'd think. It's r squared. And then the last thing is we need something so that when I have a certain mass m1 and a certain mass m2, a certain distance r apart, and I measure the gravitational force between them, I get the same number as what I would get from the calculation on the right-hand side. So I insert what I'd think of as a little fudge factor, something that I multiply by to make sure the numbers line up. It just depends on the units you're using. We call that the universal gravitational constant, and it's just this real tiny number here, which is hinting at that gravity is a pretty weak force, actually. And as it says, it is directed along the line between the two particles, so you draw a line connecting them, which there's the force mass 2 exerts on mass 1, and the force mass 1 exerts on mass 2. Which of those forces is larger? Say mass 2 is a bigger mass. Which force is larger?
2.
Nope.
They're equal
Yep. Why?
because both forces take into account both masses and the same distance.
That's one way to look at it. You could say it's because of that sort of symmetry of that equation. It doesn't matter if you switch M1 and M2. Or, third law. This is a third law pair. So, as an example, if mass 1 is Earth, or I said mass 2 is the bigger one. If mass 2 is Earth and mass 1 is the moon, the force the Earth exerts on the moon is exactly equal in size to the force the moon exerts on the Earth. Always. Again, the reason we don't see the Earth doing crazy orbits around the moon is because of the huge difference in mass. The Earth is much more massive, so it accelerates much less. It does actually technically orbit the moon in a sense. In reality, both of them orbit what's called the center of gravity of the system, and that is not actually the dead center of the Earth. It's a little bit inside it, a little bit offset from the center. And so the Earth goes on a little tiny orbit around that center of mass, while the moon goes on a much larger one around it. That's getting into the weeds, but it's interesting. All right, so what does weight have to do with this equation? It is the special case where one of those two masses is Earth. So weight is the gravitational force Earth exerts. On an object. It is a vector quantity. The direction of that vector is always towards the center of the Earth. That is the center of mass of this system, effectively. That's where the gravitational force is pulling you towards. So, if we've got an object up here, we can see it's towards the center. For something here in a minute, I'm going to sketch me as well. This is a detailed portrait of me over on the left, and apparently I'm giant. So we're going to see a simpler way we can write this law of universal gravitation specifically in the case of Earth. In that case, I'm going to say our object has mass m, or if it's me, my mass. That'll be mass 1. I'm going to separate out Earth's mass, it's mass 2. And I'll write me for Earth's mass instead of m2 to make it clear it's sort of a special thing. And then over the square of the distance. What distance? However far the object is from Earth's center. So for that ball that's held above the Earth, it's what's shown in the picture. For me, it would be instead this distance right here. All right. The mass of the Earth, so we'll know to use it in this expression, about 5.98 times 10 to the 24 kilograms. For reference, my mass is about, on a good day, 93 kilograms. So Earth's mass is astronomically larger. All right, there's another way I could write the force acting on me. Since my weight, or if I'm in free fall at least, if I jump off something, the only force acting on me is the gravitational force, I could use the second law and say the net force on me is my weight, so that is equal to my mass times my acceleration. But if that's true as well, what must be true about those two expressions?
They must equal each other.
Yeah. So if I'm in free fall, I fall off a cliff or something, my acceleration has to be this thing in parentheses. But that means if this is my free fall acceleration, which usually I use the letter G for if I'm just talking about the size of it, that letter G must equal all this stuff in parentheses. Okay, so that is a way to calculate G depending on where you are in relation to the center of the Earth. If you're further away, R gets bigger, and so G gets smaller. That's what's happening for astronauts in orbit. Their G is about 90% of what ours is. They're not actually weightless. We'll explain how that makes sense later. But if we're dealing with stuff that is relatively close to the Earth, meaning not a huge fraction of the Earth's radius, then we can just say that distance r is practically Earth's radius. Like, even if we've got something sort of floating up here, or I should say dropped from up there, it's not actually an Earth radius away from the center, but it pretty much is. All right, we can approximate and say that is about the distance for that object. In that case, meaning for stuff near Earth, we can put in the Earth's radius for little r. That's what the Earth's radius is right there. I want someone to calculate this number for me and tell me what you get. Be very careful with your exponents.
9.799.
Yeah, let's call that an even 9.8 meters per second per second. That's where it comes from. So for things near Earth, the acceleration is nearly constant because this number in the denominator is whatever Earth's radius is plus your height above Earth. That's basically Earth's radius. And we see that it depends on the mass of the Earth and its radius. That's why G is a different number depending on where you go. If you go to the moon, it has a different mass, has a different radius, and so this number comes out to about 1.6. If you go to Jupiter, it comes to like 25. If you go to the sun, it's like 275. So, it depends on where you are. But that says, we don't actually have to use this full law of universal gravitation every time if we're just talking about the weight of stuff on Earth. We can just, instead of writing this whole mess in parentheses, call it G. Weight is mass times G. That's the takeaway. Weight is, again, the gravitational force from Earth. M is your mass, or whoever's mass. G is 9.8. No negative here, because this is just the size of this force, the magnitude of it. We don't care about direction. That'll be clear from your free body diagram. So we don't want to double count it. We'll save that negative for when we're looking at specific problems. So no sign on that. All right, so let's do that for my mass up here and see what we get. So my weight would be that mass times G. So 93 kilograms times 9.8. So apparently I weigh about 912 newtons. That's not a very familiar number, so let's convert that to pounds. They're about 4.45 newtons in 1 pound. So I weigh about 205 pounds. What we're seeing there is that to get from mass to weight, there is this extra thing of multiplying by G. Mass and weight are two different things, physically two different things. And when we get back, I will try and bring in a demo to show you, like, they are literally different things, they do different things. But calculators, like calorie calculators, or if you're trying to gain weight, lose weight, whatever, they lie to you and say you could put in your weight in kilograms or your weight in pounds. They're not measuring the same thing, but secretly the calculator is doing this exact calculation to get from one to the other and saying, they're pretty much the same. I don't like that because they're not. They do different things. Weight is Earth's pull on you, mass is how much stuff is in you. They just happen to be proportional to each other. Right, tangent over on that. Time for some new ones. So we're going to talk about tension. It's actually pretty straightforward, but there is one little thing about it that we gotta make sure makes sense first. So when you pull on a rope, you know it pulls on the thing that's attached to the other end of the rope. Let's look at that in a little bit more detail. So you exert a force on the rope, and somehow at the other end of that, the rope exerts a force on whatever is attached, in this case the block. It's tempting to say those are equal to each other as far as the size of the forces. And under the right assumptions, we actually can say they're equal. But they are assumptions. This is actually not true in general. All right, when you pull on a rope, it pulls with a force of tension away and along the rope. So we'll call that tension on the block. So that's the tension force, the force a rope exerts on an object. And then we usually use tension to just mean the size of it. So throughout direction, then you just call it tension. I kind of use them interchangeably. Usually context makes it clear. So anyway, what we need to justify is that this force that you're applying to the rope is equal to the force the rope applies to whatever's attached to the other end. Let's start with the third law. So I know that when I pull on the rope pulls back on me. Those are always equal in magnitude. because of the third law. Same with the block. When the rope pulls on it, it pulls back on the rope. And so those two are always equal, again by third law. The question is really the two blue forces, or equivalently the middle blue and red force. So the force the rope exerts on the block and the force the rope exerts on you. Are those equal? Not in general, not always. But if we assume something about the rope, then we can say they're essentially equal. So that assumption we have to make is that it's a massless rope. And it is an unstretchable rope. Massless sounds pretty dramatic. I can't picture a massless rope. What it really means is that the mass of the rope is really small compared to whatever's connected to it. Essentially negligible mass. The reason we have to make that assumption is, you think about when you pull on that rope, you have to accelerate the rope itself to accelerate whatever's attached to it. That's going to take some amount of force. The amount of force required depends on the mass of the rope. And so it's sort of like you're using up some of your force. Let's say you exert a force of 10 newtons on the rope. It may be that only 9 newtons actually makes it to the block because 1 newton was used to accelerate the rope itself. If the rope is massless, or at least very small mass, we might say that I put 10 newtons in and get 9.999 newtons out the other end. Just if the mass is real small, it doesn't take a whole lot of force to accelerate the rope. Most of it goes to the block. That's the idea. If it is a truly massless rope, it takes no force whatsoever to accelerate the rope. That's second law. And in that special case, the force the rope exerts on the box is equal to the force the rope exerts on your hand, or, again, equivalently, the force your hand exerts on the rope. So, these are only equal if the rope is massless. And for the rest of forever, we're going to assume that's the case. In that case, ropes just transfer force. They take your 10 newtons you're putting in one end and transfer it to the other end of the rope. Any questions on that? Because that one is a little bit of a unexpectedly deep argument for this.
Does that say N0? I mean NZ.
N2, second law. That's my abbreviation. You'll see that pop up from time to time. I'm just saying which law sort of justifies the statement. Well, then we throw pulleys into the mix. In that case, you not only can transfer a force to another place, you can change its direction. That's the benefit of a pulley. In addition to mechanical advantage, which we don't get into too much in here, but you'll get into in like a dynamics course. The fact that you can multiply force with pulleys. Okay, so we'll make pretty much the same assumptions about pulleys, because otherwise we think, well, a pulley has mass. It's going to take some force to accelerate it. And again, I run into that problem of not all the force I'm putting in makes it to the other end. I'd have to calculate how much is quote-unquote wasted on the making the pulley itself rotate. I'm going to throw that out to make my life easier for now. We will bring it back in a good bit down the road. So we'll assume right now the pulley is massless and frictionless. So it presents no resistance whatsoever to rotation from the rope on it. In that case, again, you can say that whatever force you exert on the rope is transferred without any diminishing transferred with no change in size to the object on the other end. And even if you wrap around something, still transfers to the other end, unchanged except for its direction. Okay, we're going to put all that together into a problem, meaning the stuff about weight and the stuff about tension. Oh, I'm missing a little vector hat. And now you can kind of see how all these things come together. So what I want you to do is, once we label these forces that are acting, I'll have you draw a free body diagram and make the table that we talked about, and then we'll proceed from there. So let's first look at what forces are acting, and then I'll hand it off to you for a little bit. So we have a car engine of a certain mass. If you see kilograms, you know it's mass, not weight. If you see newtons, it's weight. Hangs from a metal ring attached to a support cable. A worker uses a second rope to position the engine above an engine compartment. What must the tensions in the two ropes be in order for the ring and engine to remain at rest? All right, so the ropes are pulling on the ring, so we should probably look at the forces acting on the ring. That'll be our object of interest here. Each rope is going to pull along its length on that rope, on that ring. I'm going to call those tension forces that the ropes exert T1 and T2. And we can see that T2, if the rope on the right is massless, is equal in size to however hard he's pulling. So another way to phrase this question is, how hard do you have to pull to guide this engine into place? That's the force that gets transferred over to the ring. Okay, and then there's one last one acting on the ring. What would that be?
The weight?
Yeah, and in a technical sense, the gravitational force on the engine is not what's pulling on the ring. It's just the fact that the engine is in contact with the ring and it has to support all that. But yeah, we're going to sort of shortcut, that's what I'm trying to say. And just say it's the weight of the engine pulling down on the ring. The ring itself will have a little bit of weight, but it's going to be pretty negligible in comparison to the weight of the engine. All right, so let's turn this into a free body diagram. We've got T1, T2, and the weight of the engine, which that's going some kind of way right now. All right, there we go. Why am I not putting the force the man exerts on the rope on here?
Because it's negligible?
It's not in this case. The weight of the ring is, but this has to be equal to this if we're saying that all the rope is doing is transferring that force to the ring. So it's not negligible. What are we looking at the forces on in this free body diagram?
On the object?
Yeah, in this case, the ring. Is the man pulling on the ring?
No.
No, he's pulling on the rope. The rope is pulling on the ring, and we've already accounted for that with T2. So that's the idea that only the forces on the object you're interested in go on your free body diagram, not just any force you can find. So we'll choose our axes here. There's not really quote-unquote convenient axes. We can only get at most one force to line up to sit along an axis. And that would be, we'll choose the weight just because then we get our normal XY axes. So we need components for T1 and T2. They tell us that this angle is 80 degrees, and this angle is 10 degrees. Let's use that to fill in our table. So we got T1, T2, and the weight of the engine. We want to use that to find our net force acting on the ring. All right, I'm going to give you 5-6 minutes to try and fill in this table with all your components. You don't have to put any numbers, just kind of, plus or minus, sine or cosine, and then the magnitude of these things, and we'll see how it went. While you do that, I'm going to drink some coffee. All right, let's start looking at components. So, start with the easy one. Tell me about the components of the weight of the engine.
0x component, and it equals to itself for the y.
Up to what in the y? Tell me about the direction.
Oh, negative.
Yep.
I'm sorry.
All right. And usually at this stage, I do go ahead and say weight is mass times g, that new relationship we found between the two, because a lot of times you're given mass and they're expecting you to calculate the weight. If you don't do that step here, a lot of times you'll use that 320 that's given as the weight. So really what you want is that times 9.8. That's your weight. So that's a tip there. All right, T1. Tell me about the components of T1.
X
There's
is
a negative.
Yeah.
Sorry,
So X is negative, I think I heard.
a positive y component.
Positive Y. Okay, and then we need T1 times something here. So what is that something for the X component? All right.
sine 10.
Yeah, sine 10. So if we look at our picture, hopefully you did sketch in the components, because you should have. Those are our two components. This is T1Y, T1X, and what we're finding right now in our table is T1X. It points to the left, and it is opposite the 10-degree angle, so we use sine. Then for T1Y, we're finding it in our Y component column. It points upwards, so positive, and then it is adjacent to that 10-degree angle, so we use cosine 10. Alternatively, you could have found that this angle is 80 degrees, and then you would have said that the Y component is T1 cosine 80. Or I'm sorry, T1 sine 80 for the Y component, and then T1 cosine 80 with a negative for the X component, but you can also just use that 10-degree angle that's given. All right, for T2, tell me about its components.
With T2, could you do T2 cosine 10?
T2 cosine 10 for the X component.
I got 10 from the 80.
Yeah.
And then that 10.
Yep, that's totally fine to do. So in that case, you would probably draw your components like this, so that the X is adjacent to the 10-degree angle, and so you would use cosine. Or if we wanted to use the 80 degree, we'd probably draw our components like this instead. It's the same two components, I've just shifted them so that I make a right triangle with the 80-degree angle instead of the 10-degree angle. In that case, I will see that T2x is opposite the 80 degree, so I would call it T2 sine of 80, but sine of 80 and cosine of 10 are the same number. So yeah, either way is fine. I'll use the 80 degree angle just for the sake of it's easier to tell which angle we're dealing with if we don't have both being 10. But you're totally free to use the 10-degree angle and you'll get the exact same answers as me. And then T2 cosine 80. All right, what's our next step?
Find the net force.
Yep, so we will add down the x column to find our net force in the x direction. I'm not going to write all that. I'm just going to say whatever I get is my net force in the x direction because I'm going to have to rewrite in a second anyway. Whatever I get from adding down the y column is my net force in the y direction. But I will carry that over to write my two equations. So my net force in the x direction is, again, I don't like negatives out front, so I'm just putting the positive thing out front. You don't have to do that. Just a weird me quirk. Okay. Now what?
We equal both to 0.
Either 0, because you already recognize that the ring is just sitting there in equilibrium, or if you're not sure at this stage, you could say mass times x and mass times y acceleration, and then stop and think about it and say, well, what's the ring doing? It's just sitting there, so it's not accelerating. So these are 0. Either way, it's the same process either way. All right, now what?
You can express T1 in terms of T2 or the other way around.
Yeah, exactly. So at this stage, we've done all the physics there is to do. We're just at algebra now. We have to solve these two equations to get T1 and T2. It's a system of two equations, two unknowns. It's painful but doable. So I'm going to take the first equation and write it in terms of T2 and then substitute that into the second equation. So for my first equation, I can say, since it's T2 blah 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 equals 0, I'll rearrange that to say T2 itself is equal to T1 sine of 10 degrees over sine of 80 degrees. I'm just solving that first equation for T2. I'll then put that in the second equation. So I'll take all this stuff and put it in for T2. So we've got T1 cosine 10 minus T1 sine 10 over sine 80. That's still just T2. We multiply that by cosine 80. And then minus mg equals 0. And then we have to solve this equation for T1. So we can factor it out of the first two terms and then bring mg over to the right-hand side and then divide by all that stuff we factored out from the T1s. We will get mg over cosine 10 minus all this mess but at least all of those things are numbers because the mass is 320, g is 9.8, and then the rest are just trig functions. So we can calculate that. We should get about 3,300 newtons. So that's the size of the tension in rope 1. And then we can take that and put it back into our expression for T2 from up above. because now we know T1's 3,300. And we should get for T2 about 580 newtons. That's really it for the problem. Let's just sort of come back and interpret a little bit. So this says T1 is supporting the majority of the engine's weight, which makes sense. You don't want to be the one holding the weight of the engine. You're just trying to guide it into place with tension T2. The weight of the engine is 320 times 9.8 mg. It's about 3,100 newtons. T1 is actually a little bit bigger than that, though. Why is T1 bigger than the weight of the engine? Okay, well, it's not only having to support the engine's weight, it's having to support you pulling on the ring with tension T2. You're pulling a little bit downwards. And so T1's having to counteract that downward pull from you in addition to the engine's weight. That's going to give a number bigger than just the engine's weight alone. Then we look at that 580 newtons you are exerting. In pounds, that's about 130 pounds. So it's still going to take a good bit of effort to try and guide that into place. But you're not lifting the total weight of the engine, like we said, about 3,100 or about 700 pounds. But it's still significant effort just to guide it into place. It's just still, you're saving yourself some of that trouble by having some sort of winch to hold it up. Okay. That's about as complex as these sorts of problems typically get for us. I mean, they can get much worse in general, and you'd see that in the statics or dynamics class. But for us, something along those lines. And that's a good place to stop. We'll finish out the chapter next class. I'll go ahead and get out the next chapter by Monday. And again, if we are back in person on Tuesday of next week, we will have our chapter 4 quiz. Are there any questions?
So when would the test be?
It's on Thursday, so on Tuesday we're going to take that quiz and we're just going to go over it right after. So we're still sticking to the schedule for everything but the quiz.
Are we still having the Microsoft Teams meeting this afternoon to review for the exam?
Yes. So that'll still be at, I think we said 3 to 4:30. So I've posted the notes for chapters 1 through 4. Hopefully you've had a chance to look at some of the practice questions. But otherwise the plan is just to do a quick recap of chapters 1 through 4 and then do practice problems, whatever ones y'all want me to do. If you're like, I can't do any more teams today, send me an email of what questions you want me to go over. I'll do that. Or just if there's concept questions, ask me about those over email. And then you don't have to attend live. It is easier to, I'll address more questions, I guess, if you are attending live, because then they'll probably pop into your head real time and I can address them as they come. All right, well, if no other questions, y'all have a good rest of your day. I'll see whoever I see, and technically not see, I guess, at 3 o'clock for the review. If you're unable to make it, just email in your questions and I will address those as well.